Okay, so today's announcements. Our exam regrades for our third midterm are due at the end of lecture. If you got them with you, you can either leave them up here or you can drop them in my mailbox in the next 10 minutes after lecture before I get back and check it. Also, the Chapter 9 sapling, because we finished up Chapter 9 last lecture, is going to be due 9 a.m. next Monday. A couple of people have asked what we're going to do to handle sort of the lag from the snow days. I'm thinking I'm pretty much just going to go through the material in order, and wherever we get to in Chapter 11 is where we get to. So once I open up the Chapter 11 sapling, I'll sort of adjust or remove questions accordingly. Okay. So FCQs are now open this week. Hopefully you got an email about that. Please fill those in. They're very helpful to me, and specifically, like, not just the numerical feedback, but if you have any like actual comments about like what worked really well for you, what didn't work at all, what you loved, what you hated. Just the more feedback I get, the more I can sort of revise how I do things next time I teach and sort of keep things like as welcoming and helpful to people as possible. So that's like a lot of changes that I made in the course, like using lecture capture and erasing the board with the bucket and everything, were based on feedback from specific people in FCQs. And also the exam regrade policy was sort of based on feedback. Okay, so a couple more things that are coming up. So this is our second to last week of classes. So the final exam is Wednesday, 2 weeks from today, 10:30 a.m. And we just got our room assignment for it. It's going to be Math 100. So not the same room where we normally take midterm exams. Definitely make sure you don't show up there. It's going to be Math 100. Also, so depending on people's availability, I know like finals are taking place over the weekend before that, so trying to schedule something on a Sunday afternoon again is probably going to have time conflicts for a bunch of people. At least that's how it's been in past semesters. So what I'm thinking is, even though Friday is a dead day or study day, no one's going to be in this room 9 a.m. on Friday. I know the time is kind of sucks being here at 9 a.m. if you don't have to for lecture, but show of hands, I guess, like, does anyone who wants to go to the study session, like, are they unable to make it at Friday 9 a.m., or does anyone have any feedback on that? Okay, cool. I'm seeing some thumbs up. So I'm going to tentatively plan on that. I will check with the scheduling office and make sure that no one has booked any special events in here then. But let's aim for that because we already kind of got the time blocked out for lecture out of habit anyway. And then I'll see if I can snag a 2-hour block like I normally do for exam review sessions. Okay. So any other questions about this or any other administrative stuff while we're on it? Okay, awesome. So last time we wrapped up Chapter 9, and so what we're going to get into today is Chapter 10. Okay. All right. I think in the notes I shuffled stuff around and reordered it a little bit in a way that actually makes the start of the notes a little bit confusing because I don't actually say alcohols and thiols in the first paragraph. But that's kind of, just as a quick review here, I'm going to have to fix this in the notes, but alcohols are anything with an alkyl group attached to an OH, and thiols are the sulfur equivalent, RSH. Okay. So the first thing that we're going to start out looking at here is actually just a throwback to acid-base behavior, because this will actually explain a lot of things that they do in more complicated reactions in the chapter. So as a reminder, alcohols, ROHs, have pKa Usually about 16 to 18 is most common. There's a few outside that range in either direction. Actually, I think, so 16 to 18 is the most likelihood, most commonly given range. A better sort of expanded range that covers just about everything is 15 to 19. Okay, so thiols have pKa's usually about 10 to 12. Okay, so in other words, the proton comes off of a sulfur a little bit more easily than it comes off of an alcohol, which totally makes sense, right? If you guys remember that cardio acronym from chapter 3, oxygen and sulfur are in the same column of the periodic table, so sulfur being a larger atom is going to be better at stabilizing a negative charge and be a little bit more acidic. Okay, so if we take one of these things and pull in a proton off of it, we're going to get RO minus. We've seen that a bunch already because it came up as a pretty commonly used reagent in chapter 9. So these are called alkoxides. So some examples are like sodium ethoxide. Or TBUOK, tert butoxide, or potassium tert butoxide. Okay, so we've been using these for a little while now in chapter 9, but how do we actually make these things? Okay, so the easiest way is actually some pretty old school chemistry. We're just going to deprotonate it with a stronger base. But we want that base to be something that doesn't stick around and cause problems and like leave other stuff mixed in with the alkoxide. So the easiest way to do that is, say we've got this alcohol here. We're going to use NaH. We're kind of used to seeing hydrogens act like protons where they take on a positive charge. But if you look at this, sodium is actually less electronegative than hydrogen. So this is actually sort of equivalent to like an organometallic in that you've got something that's so non-electronegative attached to it that something that we'd more commonly see with a positive charge actually ends up taking on a negative charge instead. So this can split into H minus and Na plus. So this is called sodium hydride. Okay, so the H plus is a pretty strong base. pKa usually cited as like mid-30s. So let's use 35 as kind of a ballpark figure. Okay, so what's going to happen is that hydride is a strong base. It goes in, pulls off the proton from wherever it's deprotonatable. I'm just going to redraw it over here. So the hydride comes in, takes a proton, and you end up with O minus, and now you've got an HH molecule that you just formed, plus sodium plus is still hanging around as the spectator ion. Okay, so the whole reason we choose to use sodium hydride is because the other byproduct of this acid-base reaction is hydrogen gas, which immediately leaves the reaction so it doesn't stick around and cause problems. And on top of that, having it leave the reaction means that this reaction is irreversible. Like there's no way for it to do the reverse reaction because there's no longer any conjugate acid around to get deprotonated, even if pKa's were favorable for that. Okay. So a lot of the time the way that you'll actually do this reaction is you'll just have some flask of whatever alcohol you want to deprotonate. You'll throw in a little bit of sodium hydride and you'll end up with the alkoxide still floating around in a whole lot of the alcohol molecule. So if you remember in chapter 9, a lot of the time if we were using, say, sodium ethoxide, NaOET, the solvent that we used for that most of the time was HOET, right? Like the conjugate acid of that. And that's because when we make it, there's usually going to be a bunch of that alcohol still around as the solvent. So that's like the cheapest and easiest way to do it. Okay, so questions about that? Okay, cool. So that's one way to do it. The other, even older option is instead of using sodium hydride, we can just use sodium metal. The mechanism for this, it's kind of similar to Grignard formation or organolithium formation, but we're not going to get into it. If you look at sodium on the periodic table, it's got one unpaired electron just like lithium does. Mm-hmm. Okay, so in this case, if you want to get an actual balanced reaction, which we're usually pretty careless about doing in OChem, technically one equivalent of alcohol is giving you half of one equivalent of hydrogen gas. So it would take two molecules together, both giving up their hydrogens to get one molecule of H out of that. Okay. So this is a little bit cheaper and easier to do in the lab in some ways, just because historically sodium metal was a little bit easier to make than sodium hydride. But most of the time now, sodium metal is a little bit more inconvenient to slice little bits off of. Sodium hydride is a nice convenient powder that you can weigh out easily. Okay, any questions about either of those options? Okay, cool. So then one last thing is looking at this for sulfur. So deprotonated RSH, deprotonated thiols, are called mercaptides. So you can make them by either of the above methods, which also work fine, or you have a third option. Which is, we know that SH is more acidic than OH, so we can just make an alkoxide first and use that to deprotonate the sulfur. So if we do like whatever thiol and whatever alkoxide we just made using one of the previous methods, we can just have this come in, take an H off of there, and this is in equilibrium, but it favors the products pretty strongly. So we could make it that way. Okay, so this is kind of how we get some of the tools that we used in the previous chapter that we can now go and do stuff with like alkyl halides. But we can do a bunch of other things with these reagents too. Okay, so one last thing we're going to cover in this section. Most of the time we're going to see, actually that's not true. We're going to see pretty frequently alcohols getting turned into bases. But we already know that alcohols are amphoteric. They can act as either an acid or a base. So what if we kind of put them in an opposite type of environment? So rather than taking away a proton, we can also add a proton. If we use, say, H2SO4, this is a reaction that we're going to see pop up a bit in this chapter as well, is turning it into a positive oxygen instead of a negative one. Okay. So, kind of a big theme of the first half of this chapter is we can do a lot of the same chemistry from chapter 9. Which is alkyl halides. So we can do SN2, we can do SN1, we can do E2, we can do E1 on these alcohols. But the problem is, or I guess the difference is that OH is not a good leaving group on its own. So we have to convert it to a good leaving group first. Okay, so there's several different ways to do this that we're going to cover. And once we have that on there, once we have OH converted to a leaving group on the molecule, then we can just straight up pick and choose any of the main reactions from chapter 9, just based on what else we hit that molecule with. Okay.
How favorable is it to have that positive charge on the O?
I guess it is more favorable than having sulfuric acid around. Yeah, it's like still an equilibrium thing, so depending on concentrations, you might still have most of the molecules be in this form, but you know, enough of them at any given time might look like this that you could still make a reaction happen if you wanted to. Yeah. Okay, so that's actually what we're going to look at first here, is acid catalyzed eliminations. Okay, so the simplest and easiest way to convert OH to a good leaving group is doing exactly what we showed up here and sticking a proton on it. So we're going to throw in a strong acid, usually H2SO4. And let me do the overall reaction first, because there's something interesting worth pointing out about this. Okay, so we take an alcohol here, we hit it with H2SO4, and it turns out elimination usually ends up being the major product instead of substitution, for reasons we'll get into in a second here. Okay, so we're doing an elimination, we're making a double bond here, but we've seen the exact reverse of this reaction way back in chapter 4. If you look at it, if I start with an alkene and water, and I use H2SO4, then I am doing acid catalyzed hydration of an alkene. So then the question is like, okay, H2SO4 makes it go in one direction, and H2SO4 also makes it go in the opposite direction. How do I pick and choose what actually is going to end up happening with this thing? Turns out, if you remember from Gen Chem, you guys covered Le Chatelier's principle. Yeah. So basically, if a reaction is producing, say, a byproduct like water, and you continually pull that byproduct out of the reaction, you can force all of the rest of the molecules to get sucked over to the product side. So in other words, if you want it to go all the way to the alkene side of the reaction, remove as much water as you can, and that forces everything else to sort of end up as an alkene. So on this side, we want to remove H2O to drive to the alkene side. On this half, like when we did this in chapter 4, we want to add as much water as we can, and then Le Chatelier is going to tip it so that it favors the alcohol more. Okay, so adding water is pretty obvious. You put water in the flask. What options do we have for removing water? Yeah. You could if the boiling point of this were not lower than water. But that actually is one other option, is that rather than removing water, you can actually distill off the alkene as it forms, which if you guys remember the experiment you guys did in lab, actually right the week before break, distilling off the alkene is another option to get it purified. Or to drive towards the product side. So let me write that up here. Okay, so the alkene being lower boiling is easier to pull out of the reaction. Sometimes that might not be the case, especially if it's a much bigger molecule. So in that case, we need some good way to sort of lock up the water as it's forming. So we're going to see a few options later on of good ways to remove water from reactions. But one option is a lot of concentrated acids, especially H2SO4. This is actually strongly dehydrating. So concentrated H2O4, if you get it out of the bottle, is about 4% water, and the rest is actually like H2SO4 molecules itself. So this is actually going to prevent the H2O from having any energetic incentive from reacting to form the alcohol. I think, I don't actually list these in the notes yet. I think it's later on in the chapter. But I'll just throw it up here since we're on the topic. One of them is these things called molecular sieves. Or mol sieves. And these are these weird inorganic kind of clay beads that are usually like pretty small little white pellets that you add into the reaction. And their whole deal is that they have these tiny little channels running all through the material that happen to be about the right size to let a water molecule go in there and then bind onto it pretty strongly. So the channels are about 4 angstroms. And so 4 angstrom molecular sieves is often how you'll see that written on the arrow. So a lot of the time you'll see 4 angstrom molecular sieves to soak up water there. There's a few other older options, like there's specific pieces of glassware that are designed just to trap the water that phase separates out and isolate it from the rest of the reaction. But this is probably more commonly used now. Okay. So any other questions about this before I get into the mechanism? Yeah.
Can you use like a drying agent, like a salt?
You can, although sometimes they, yeah, I guess they're less popular for this, and I'm just trying to figure out like if they would cause any other side issues. None that I can think of right now, so I think that would also work okay. Yeah. Okay. So yeah, just any way that you have of locking up the water so it's not around to force the reverse reaction. Okay, so the mechanism for the forward direction that we're looking at now, the acid catalyzed elimination, is actually exactly the same as the reverse reaction, just in reverse. So if you sort of started at the end here and drew out all the intermediates in reverse order, you would hit all the same intermediates that you do in the forward order. All right, so we already know that OH is going to be able to pick up a proton if there's a strong acid around. Which gets us to here. What we've done now is actually, if you look at this OH2 plus group, this is actually quite a good leaving group. If you tried to kick out just OH as it is now, it would take a minus charge. It would be a pretty strong base as it leaves the molecule. Here though, if you kick out OH2, it's neutral after it leaves. And so, just to write it up here, OH2 plus is a good leaving group. Because it's leaving as neutral water. Okay, so this can drop off pretty easily on its own, and now we're looking at an E1 type mechanism. All right, so you got a carbocation there, and then water or whatever else is around can come in, pick that proton off, and form the alkene that way. So if you look at this, after you get a good leaving group on the molecule, this step where you lose the leaving group and then this step where you deprotonate is all just E1. It's just getting to that point, we have to protonate the oxygen first. Okay. But then also it looks a lot like this stuff from chapter 4, just in reverse. So if you remember chapter 4, acid catalyzed hydration, you start with an alkene, then you go to this thing where one carbon has a proton and one has a positive charge, and then the water sticks on and you go to this thing where you've got a proton and an OH2 plus on there, and then you go to this where you've just got an OH and an H. So the arrow pushing is going to be different because the steps look different in the forward or the reverse direction, but every intermediate is going to be the same in the forwards and backwards direction. So this is actually sort of a general rule. I think the principle of mechanistic reversibility, which is that the forward and the reverse reaction always go through the same sort of set of intermediates because that happens to be the lowest energy pathway between one end and the other of the reaction, no matter which way around you draw it. Okay, so one last thing about this. When we are looking at E1 normally, does it tend to go Zaitsev or anti-Zaitsev? Zaitsev, right? Same thing here. So if we have this, it's going to give the more substituted alkene as the major product and the less as the minor. Okay, cool. So that's pretty much it for this reaction. Like a lot of other acid catalyzed things, there's a few pitfalls, like you have to watch out for carbocation rearrangements, stuff like that. But this is probably the cheapest and simplest way to do it if it happens to work for your molecule. Okay,
Are there kind of exceptions to the mechanism where the forward and the reverse would go through the same intermediates based on the activation?
Generally no, just because like so long as your starting point and your ending point is the same, like the shortest route between the two always happens to be sort of the same, as long as it's a reversible reaction, like both directions will do that. If there's some really strong energetic drive that like forces it to go one way and then like it's unlikely to reverse itself, then that might sort of, I guess the steps would hypothetically be the same, just at some point there's such a big jump in energy that it's never going to like bridge that gap and jump back up where it came from. Yeah. Okay. So that pretty much wraps it up for acid catalyzed hydration, acid catalyzed elimination rather. That's kind of one way to convert your OH group to a good leaving group. A little bit more sort of delicate and universally applicable way involves not beating your molecule over the head with H2SO4. So what we're going to look at now is converting alcohols to either actual alkyl halides, so just dropping us straight into the alkyl halide chapter at that point, or what are called pseudohalides, which we haven't seen before. Okay. So first up, what we can do is just straight up convert our alcohol to an actual halide. And one option for doing this is reacting it with HX, so like HCl or HBr. So this is going to look a lot like SN1 or SN2, but just like above, you got to protonate the OH to make it leave. So if you take this and react it with HX, you're going to get a halogen on there a lot of the time. Okay, so mechanism for this is going to look like that OH has to pick up a proton. So we're on a primary alcohol here. Does SN1 or SN2 sound more likely for this? SN2, right? Yeah, because this is pretty sterically unhindered. So at this point, Cl minus can come in, do SN2, kick out that leaving group, and get you on here, get on here. So this is generally going to be SN2 for methyl and primary. I'll draw the mechanism for secondary and tertiary in just a second over here, but does anyone have any questions about this example first? Okay, cool. I'm just going to erase the board then. Okay. So we can also look at this reaction happening if we're doing it to a secondary or tertiary, in which case it goes by an SN1-like mechanism. So pretty much starts out the same way. You protonate the oxygen, get it to here, and now instead of a concerted substitution, it's doing a stepwise substitution where that drops off first. You get a carbocation, and now the halogen can come in and attack. So SN1 for secondary and tertiary, in other words. Okay, so pretty much this is in line with what we would expect from chapter 9. Just again, we have to get the OH to be a good leaving group before it'll play along with whatever nucleophile that we have around.
Why does the OH2 group have to drop off first?
So just like we saw for SN1 in the last chapter, the halogen, or whatever leaving group that we've got on here, I guess for one thing, it has to get out of the way before the other group can come in just because of sterics, because SN2 is impossible. But the leaving group can actually sort of like partially dissociate itself and then stick back on. And that's actually happening more frequently the more substituted the carbon is and the better the carbocation is. So this, or like any other leaving group on this carbon, might like drop off, stick back on, drop off, stick back on, drop off, stick back on. And then at some point it's going to drop off. And then while it's gone, the nucleophile that happens to be around now is like, aha, and jumps on that carbocation. And that's how you get the substitution pattern. So. Okay, so that's less likely for primary and methyl because they make bad carbocations, so it's dissociating less at any given time. SN2 would be yes. Yeah, so you may have like a no reaction kind of situation if you've got a bunch of steric hindrance nearby. Yeah. Okay. Alrighty, so any other questions about this, which again kind of ties into last chapter a little bit? Okay. All right, so in the last couple minutes that I've got left, let's look a little bit at pseudohalides because those are really cool and useful. So pseudohalide is kind of a nickname for sulfonate ester. pseudo means false or like fake. So pseudohalide is like a fake halogen or something that looks like a halogen but isn't. Okay, so there's 3 of these that are really commonly used. I'm going to draw all 3 of them out. So one option is this. So this one is a mesyl or MS group, which means that this whole thing, including the O, is an OMS. So what we've done here is make a mesylate. Or ROMS. Okay, you'll notice that all 3 of these actually have the common pattern of R attached to O, attached to a sulfur with 2 oxygens double bonded to it. So the only difference is the R group at the back here. So we've got methyl group, gives us mesyl. That's actually short for methyl sulfonate. This one is a toluene sulfonate. Which gets abbreviated as TOSL or TS, which means that this group, including the oxygen, is OTS, or this whole molecule is a tosylate, ROTS. Okay, and then the third one that's really commonly used, again, has that same pattern of R, oxygen, sulfur. But what it has out at the end is a CF3 group, so trifluoromethyl sulfonate, or write that out. Or triflyl, or TF, which means that this whole thing is an OTF, or the whole molecule is a triflate. Okay. Okay, so the cool thing about the mesyl or the tosyl or the triflyl groups is that all 3 of them are pretty similar to halogens in terms of leaving ability. So mesyl and tosyl are actually about as good a leaving group as bromine. And triflate's even better. It's about as good as iodine. Okay. So part of that just has to do with when you kick the group out with a negative charge, it's real stable with that negative charge. Let me just draw that up here real quick before we break. So all 3 can stabilize their negative charge by resonance. If you were to kick out your leaving group here, say you are doing an SN1 or an E1, let's just make it SN1, you're leaving your carbocation and you're leaving your leaving group. And so if you look at this thing, it's got 3 options of where to put that negative charge because it can do resonance of kicking the negative charge up onto that oxygen, which gives it 1 more position to put it, or it could kick it down to the bottom oxygen, which gives it a 3rd position to put it. So it's pretty stable. Okay, so that's why they're good leaving groups. Okay, so I'm going to wrap up here and then we'll cover how to actually put these on the molecule next time.